Welcome to the Axiam CFM56 geometric balance engine core high side assembly process. You will see a demonstration of parts measurement, rotor assembly, rotor mating, blade measurement and labeling, and blade distribution. Axiam's assembly processes are always repeatable and result in optimal straight builds of the engine core modules about the actual center line of rotation for each set of parts. Axiam allows you to get direct control over process and part dimensional variation. Axiam's assembly processes are custom developed for each engine model and engine shop. The goals are to make the engine shop more competitive by delivering productivity, improved engine performance, maintenance cost savings, as well as assembly and balance process improvement and control. Two families of products are offered: Geometric Balance Engine Core Assembly Process, referred to as GeoBal, and Engine Core Restoration Assembly Process, referred to as ECR. GeoBal is shown in light blue, green, and brown. GeoBal optimizes shop productivity and engine performance by building straight rotors about the actual centerline, mating rotors to their shaft or other rotors, building bearings and seals optimally, building casings straight so that their concentricity coincides with the actual centerline, and distributing blades about each disc's actual centerline to offset unbalance, including fan blades. A GeoBal engine core build results in optimal blade tip clearances for each rotor disc of a straight engine core, which optimizes engine performance for each set of parts. ECR is shown in light blue. ECR is used for the assembly of straight rotors about the actual centerline of rotation and the optimal mating of rotors to their shaft or to other rotors. Of the three build methodologies currently in use, only Axiam consistently builds straight rotors with each rotor stage built to its centerline and engine cores built about a common centerline of rotation, which helps preserve engine performance on wing. The engine manual and bearing-to-bearing methods produce bowed rotors despite a rotor being within the maximum runout limits at its endpoints. The difference in methodologies enables Axiam to generate SFC, EGT, and vibration improvements compared to the other methods. There are three stages to consistently optimal and repeatable engine core builds: development of an optimal predictive build model, performing actual builds to match the model, and performing ongoing maintenance and assembly balance process engineering support. To generate optimal predictive build models in Stage 1, part measurement data accuracy 1 order of magnitude greater than the desired measurement is required, without any data corruption from uncontrolled measurement variables. A different optimal build model is generated whenever a part is modified or replaced. Axiam provides a number of scalable gauging systems that range from small tabletop gauges for use with space shuttle turbine pumps to very large floor model gauges for use with industrial turbines, all with at least a volumetric measurement accuracy of 20 millionths of an inch, automatic tilt and centering correction software, and part distortion correction software. All gauges require only 4 to 5 minutes for setup and measurement of a part. Part distortion is mathematically corrected by Axiam's biplane deviation measurement software, a proprietary measurement calculation. This software simulates the part measurement as if the part were in a constrained state, as in a rotor assembly, rather than a free or unconstrained state. Part distortion correction is necessary to create optimal build models. Axiam's tilt and center mathematical algorithms are accurate to 1 millionth of an inch. This software, together with Axiam's proprietary gauge tooling, allows part setup and measurement to consistently take 4 to 5 minutes. Axiam provides a full set of gauge tooling and fixtures to hold parts and rotor assemblies for the measurement of specific engine models. The SuperStack software computes, from the part measurement data, a 3D homogeneous vector best fit of the parts, resulting in an optimal straight build. In Stage 2 of the repeatable assembly process, operators will use custom tooling and proprietary procedures to build engine core modules that match the optimal predictive build models. Axiam's family of predictive software applications consists of SmartStack software to build optimal straight rotors, ShaftMate software to optimally mate a rotor to a rotor or a rotor to a shaft, Bearing Stack software to optimally build and align the bearing compartment's static structure, dynamic structure, and seals, SmartCase software to align the casing concentricity with the rotor and shaft centerline, and SuperStack software to optimally distribute blades about each rotor disc to offset its unbalance, as well as optimally distribute fan blades. Parts program software that uses part dimensional information to calculate the best fit assembly. Axiam designs and manufactures custom hydraulic assembly tools. This rotor build tooling ensures the proper seating of rotor assemblies or subassemblies. It also prevents the shifting of rotor parts when the engine is in the test cell or on wing. Consequently, test cell rejects due to vibration are eliminated. Axiam provides photo-illustrated manuals with procedures for engine core gauging, marking, and assembly, which is integrated with the engine manual procedures. In order to ensure ongoing optimal performance of its repeatable assembly process, Axiam installs the equipment in the engine shop and trains shop personnel. Continuing maintenance is provided through the Technical Service and Engineering Support Program. Axiam calibrates and certifies its measurement gauge systems, hardware, and software in accordance with ANSI, FAA, and military specifications requirements. Its 3D calibration and certification master emulates the geometry of the engine core parts being measured. This master is the only OEM and FAA-approved method for gauge system certification. As this is a production gauge, part setup needs to be both rapid and accurate.
The first part to be gauged is the 4-9 drum. The drum is placed on the dedicated chuck jaws. Once the probes are within range, the inspection can begin. The table is rotated to the 0 angle and a 0 line is marked on the part. The measurement results are shown for the part in numeric form. The alternate results are mathematically corrected for part distortion. The measurement results can then be shown graphically. The red profile illustrates part distortion generated by manufacturing using a fixture that distorted the part during machining. The on-the-screen measurement allows the operator to measure the distortion and print out the plot. In the lower right-hand corner of the plot page, in the yellow box, is the measurement results. The next part to be gauged is the forward shaft. There are two sets of measurements done on the forward shaft. The first now being shown is the measurement for installation of the stage 1-2 discs. The second set of measurement data will be used to assemble the CDP seal 4-9 drum, stage 3 disc, and the forward shaft. The next part to be gauged is the stage 3 disc. This disc is generally distorted, so the proprietary Axiam biplane deviation measurement is a very important component. This measurement mathematically removes the part distortion and calculates the part geometry as if the part were assembled. The measurement results page shows the standard part measurements. The alternate results page shows the part distortion corrected measurement results that will be used in the assembly process. The two faces are shown in yellow and green. You can plainly see the part distortion. However, the yellow and green profiles track each other, indicating the part is distorted, but both faces are parallel. The top face runout of the third stage disc is shown in the top page, outlined in yellow. The runout is calculated as 1,157 millionths of an inch with an associated angle of 115 degrees. In the lower yellow block is shown biplane deviation computation to remove part distortion. Notice that the corrected runout and runout angle are completely different. After mathematical processing using the Axiam proprietary biplane deviation correction software, you can see in the lower yellow box the biplane deviation is substantially different for the amount of face runout and the associated angle. The first and second stage disc is then measured. The last part to be measured for the assembly is the CDP seal. The next step is the operator calls up the Axiam SmartStack software program. The measurement data for that module is automatically loaded into the program. The software then does a 3D homogeneous transformation calculation in order to establish the position of each part in the assembly, resulting in the straightest rotor. After calculating, the software will then tell the assembly person at what bolt hole each component should be aligned. This will become the stacking axis. The software will then also predict the centerline deviation at each stage of the assembly and display the max centerline deviation of the entire assembly. Each part is marked with a bolt hole location for assembly. We refer to this mark as the stack line. The next step is the module assembly process. The top plate of the hydraulic tooling is attached to the rear of the 4-9 drum with a set of bolts. As per the CFM instruction manual, heat the rim of the front shaft until it seats on the 1-2 stage flange. The 3rd stage part has been in the oven and heated to 210 degrees Fahrenheit. This stage is then removed from the oven and mounted to the forward shaft, aligning the stack lines. Immediately mount the 4-9 drum onto the 3rd stage, aligning the stack lines. Once the 4-9 drum is seated, the threaded shafts are inserted into the assembly tooling top plate. The split nut is mounted to each rod and manually tightened. The next step is to apply the hydraulic pressure to the tooling. The hydraulic pressure will be maintained during the bolting process. The hydraulic pressure is very important, as the 3rd stage disc distortion will cause the parts to separate and the bolting will not fully seat the parts, resulting in a possible rotor shift problem. The bolting is done to CFM specifications. Once the HPC is completed, the assembly is mounted to the gauge for final inspection and comparison to the SmartStack model. Mount the CDP seal to the assembly, carefully aligning the stack line. After the compressor is completed, we will move on to the high-pressure turbine. The first part to be measured is the rear shaft and bearing housing. The rear bearing mount has an interrupted surface, as shown here. The Axiam measurement software automatically removes the interrupted surface data. The second part shown here to be measured is the high turbine. The third part to be measured is the forward turbine seal. The last part to be measured in this assembly is the front shaft. As you can see, the red and blue diameter profiles representing the two diameters are severely distorted. This shows why it is important to use centerline deviation instead of the far less accurate and deceptive runout measurement. This green is showing the ability to measure a feature's distortion on the graphic output page. The red diameter is elliptical in shape and out of round by 0.002, as shown in the bottom right-hand corner of the screen. The blue diameter distortion is multi-lobed, causing more difficulty in determining the angle and the maximum runout. The maximum distortion is shown being measured on the screen, with the results shown in the bottom right-hand corner. Once the measurements are completed, the data can be automatically loaded into the stacking software program, as shown on this picture. The software will then do a 3D best fit of all the parts in order to establish the straightest assembly. The software displays the angle of each part and the associated bolt hole. The second page of the Smart Stack program shows what the geometry of the assembled rotor will look like, including the predicted centerline deviation of the rear bearing. The next step is the assembly of the rotor, and in that process we mount the front shaft to the build fixture. The front turbine seal is then marked with a stack line which represents the bolt hole location as described in the Smart Stack program. The bolt hole or stack line is then marked on the rear shaft. The last part, the turbine, is marked with the correct bolt hole location. Once the stack lines are marked on all the parts, dry ice is put in a plastic bag and distributed around the flange of the front shaft. This is described in the CFM manual. Once the front seal has been installed, the seal rear snap is heated per the CFM manual. Immediately after heating the seal's rear snap, the turbine is located with the stack line aligned. Once the components have been assembled to the stack line, the top tooling plate of the hydraulic fixture is located on the stack. The rods and split nuts are then mounted onto the fixture and hydraulic pressure is applied. While the pressure is maintained, the final bolting of the assembly can be accomplished as defined in the CFM manual. After bolting of the assembly, the HPT is mounted to the Axiam GMS 4060 gauge and the model prediction is verified. At the same time, the computer will generate measurements that will be used for mating the HPC and HPT, resulting in a straight high rotor. Once the two modules have been verified and the measurements taken for module-to-module best fit mating, the next step is to call up a software program called ShaftMate. This program will calculate a best fit for the two modules that will result in the straightest high rotor assembly. Once the computation is complete, the software will then show the results page. This shows the module-to-module assembler how to clock the modules to each other. As shown, the turbine will be located at 217 degrees from the compressor's zero or stack line. The bolt hole of the turbine that coincides with the compressor is hole number 29. To reduce possible confusion, the alignment is also shown graphically. As shown here, the GeoBal program begins with a Smart Stack calculation, which produces an optimal and straight rotor. This calculation establishes the centerline and angle of each disc or drum rotor blade slot. This is showing a setup and run page for measuring the individual parts in the module on the Axiam gauge. The next step is to weigh the blades either by pan weight or moment weight. The weighing is completed on the scale connected to the Axiam computer. The operator enters the part number of the blade and the serial number of the blade. If there is not a serial number already assigned to the blade, the software will automatically assign a temporary serial number. At this point, the blade is placed on the scale and it's weighed, recorded, and stored. The information for every blade will automatically be stored in the database for future use. The blade is moved to the inkjet blade marking system. The blade is placed on the sliding table and moved under the printer. The printer marks the blade with a temporary serial number, weight, and a scannable barcode that contains this information. A set of blades can be assigned to a particular disc or drum rotor or be stored in the general blade database to be assigned at a later time. The inkjet printing does not leave any raised areas on the blade surface. Back in the rotor assembly area on the main Axiam computer system, the operator opens the geometric balance program from the drop-down menu. He can then load a particular set of rotor assembly information, identified by engine model, part number, and serial number. The software performs a calculation of the smart stack assembly that will realign the center of rotation based on the bearing journal or appropriate diameters that generate the engine centerline. This new calculation will use centerline deviation of each stage in the rotor and its associated angle to optimize distribution of blades. On the GeoBal input page, blade data can be loaded by calling up the complete blade set already assigned to the rotor from the database, or individual blade information can be loaded by a barcode reader if the blades have not yet been assigned to a particular disc or rotor. This page shows the list of blades along with serial number and weight data. Once all the blade data is loaded into the program, the GeoBal calculation can begin. After the calculation has completed, the program will display the sequence of blades assigned to the appropriate location on a stage-by-stage basis.
This concludes the demonstration of Axiam's CFM56 geometric balance assembly process.